problem 12.11. We have a random sample of size n from this exponential distribution. We want to use them to make this test. And the null hypothesis is theta equals to theta 0. Now alternative hypothesis is theta equals to theta 1 for this parameter theta. Okay, use the Neyman-Pearson lemma to find the most powerful critical region of size alpha. So we know that the form of that critical region is this. So we need to choose the case such that this critical region has a size alpha. And then the Neyman-Pearson lemma will guarantee that this is the most powerful critical region of size alpha. So to find out this ratio, we just need to look at the PDF of the exponential theta, which is this. And then L0 is just the joint PDF of the random samples where we assume theta to be equal to theta 0 as given in the null hypothesis. So that will be just the product of their distributions, and where we'll get this, where theta is equal to theta 0. And similarly, we can get L1 where theta is equal to theta 1. Okay, so that is L0 and L1, and then the ratio of these two guys will be just this, and the critical region should be this less than or equal to some k, and that will be the form here. In other words, we can also write it as a form of this thing. We can solve for this thing from the equation inequality here. We get that's equal to greater than or equal to this thing here. Okay, so now while we're doing this, this can help us to figure out the value of k, because we need to find the k such that this region, this critical region, has a size alpha. So why this is going to help us? Because the xi's are following the exponential distribution. So if xi's are following the exponential distribution with theta as a parameter, remember that this is essentially just this exponential distribution is a special case of the gamma distribution, the gamma with the 1 as the alpha and the theta as the beta. And now if you have those as IID gamma with the same theta, then the sum of xi's as a property of the gamma distribution, the sum of this IID gamma will be following the gamma again following the gamma distribution with n and theta as the parameters, alpha and beta. Okay, so that means we know the distribution of the sum of xi. So the probability that the sum of xi greater than or equal to this value is equal to alpha means that this is the value, this is the critical point or critical value y of alpha, so that this, let's say this is the gamma and theta. Okay, so we will need to choose, if the y is following this, then we're going to find this y alpha here, so that this area here is equal to alpha. Okay, so this y will be our sum of xi's. Okay, so we just need to find out this value y alpha, which is possible now because we think, since we know the n, we know that for any particular theta, this will be, say, this will be this is assuming that this is following a particular theta, say theta 0, then that will be 0. So for the theta 0, we know the distribution of the y, so we can actually get the area here, and make sure that choose the y alpha so that the area here is equal to alpha. That will be our y alpha. So we just need this sum, which is our capital Y here, greater than or equal to y alpha, then the probability will be automatically equal to alpha, right? So that is what is here. So the probability of this greater than or equal to this, which is this is essentially just equal to the y alpha. The probability of this greater than or equal to y alpha equals to alpha, and that's how we're going to solve for this k. Okay, so we can either just directly do this, just say that okay, our critical region is just the sum of this greater than or equal to y alpha, or we can get back to the original form where we say that okay, the critical region is given by this ratio less than or equal to the k. Okay, these two are equivalent because we actually get this sum of this xi greater than or equal to y alpha from this inequality. Okay, so either way will work, but apparently this will be simpler, right? So, but either way they are equivalent, and they're all giving us a critical region of size alpha. So it just depends on which test statistic you want to use. You want to use this as the tested statistic, which is the lambda of x we discussed in class, or you can just simply use the sum of the xi's as your test statistic. Okay, and they correspond to a certain critical region, but these two are equivalent. And yeah, that's how we get this most powerful critical region of size alpha.